All right, in this video, we're going to talk about section 7-2 dealing with operations on decimals. And in this video, we'll use concrete models, drawings, strategies to develop efficient algorithms for decimal operations. Also, we'll convert from scientific notation to standard numbers and vice versa, and also apply strategies for decimal mental computation and estimations. All right, so first of all, we'll talk about adding and subtracting decimals. So let's consider this sum, 2.16 plus 1.73. And here we can use base 10 blocks to demonstrate such an addition problem, okay? So like in this case right here they're using 2 flats to represent the number 2, the 1 long to represent 1/10, and 6 unit cubes to represent 1/100, or 6/100 in this case. And then we're going to add to it 1 long, 1 flat, 7 long, and 3 unit cubes for 1.73. And that sum would be this. We'll have 3 of the flats, 8 longs, 9 unit cubes. And that represents, in this case, 3.89. Okay. So here we can change the problem to one we already know how to solve. That is a sum involving fractions, like in this case right here. If we got 2.16 plus 1.73, we can write this in fractions, like the 2 would be just the 2 itself, plus the 1 is in the 10th place, that'd be 1/10. 6 is in the 100th place, that'd be 6/100. So it'd be 2 plus 1/10 plus 6/100. And then plus the 1.73, that's 1 whole, 7/10, 7/10, and 3/100, 3/100. So here we just group the whole numbers, group the fractions with the denominator of 10, and group the fractions with the denominator of 100. So 2 plus 1 will be 3, 1/10 and 7/10 is 8/10, 6/10 and 3/10 is 9/10. Converted back to a decimal would be 3.89. Okay. And of course, when we add decimals, we simply just line up our decimal points and then just add column by column with regrouping if necessary. So in this first homework example, we have this. Hannah went to the store and bought a chair for $19.04, a rake for $13.33, a spade for $13.62, a mower for $135.34, and 2 6-packs of water for $2.98. What was the bill? So it's just a simple addition of just numbers with decimals in it. So we got 19.04, then 13.33, and then 13.62. And then the mower was $135.34. 2 6-packs of water for $2.98 each. So we need to write $2.98 twice. And then we just simply add column by column to get our answer. Okay. So if I add 4 and 3, that's 7, plus 2 is 9, plus 4 is 13, plus 8 is 21, plus 8 is 29. So we bring down the 9, regroup with the 2, 2 plus 3 will be 5, plus 6 is 11, plus 3 is 14, plus 9 is 23. 23 plus 9 is 32, so we write the 2. We group with the 3. 3 plus 9 is 12. 12 plus 3 is 15, plus 3 is 18, plus 5 is 23, plus 2 is 25, plus 2 is 27. Write down the 7, carry the 2. 2 plus 1 is 3, plus 1 is 4, plus 1 is 5, plus 3 is 8. So we write down the 8, and then we just bring down the 1. Also, we bring down the decimal point. So the decimal point will be between the 7 and the 2. And since we're dealing with money amounts, I'm going to put a $sign here. I should have put one at the top. So the total bill was $187.29. Okay. All right, here's another example. A bank statement shows a checking account with a balance of $53.54. The balance recorded in the checkbook shows only $20.59. After checking the canceled checks against the record of these checks, the customer finds that the bank has not yet recorded 6 checks in the amounts of $3.16, $5.51, $3.35, $15.49, $8.36, and $3.64. And really the question to that would be, is that bank statement correct? Well, is the bank record correct? Okay. So I just add that, is the bank record correct? Okay. And if it is, the bank statement is correct. But if it's not, then how much is the bank over, or how much is the bank under? So we need to add the checks that have not yet been recorded. So that's $3.16, $5.51, $3.35, $15.49, $8.36, and $3.64. Okay, and we're going to add those numbers together. And of course, for the sake of time, I'm going to use the calculator to add those numbers up. And assuming that I did this right, this is $39.50. Okay. So the total of those checks is $39.50. Now, in this case here, the balance recorded in the checkbook only shows $20.59. So if I add $20.59 to the checks that are outstanding, that's $39.50, I will get $60.09. Now, is this amount the same as the statement from the bank? Well, by looking at that, that answer would definitely be no. And in this case, I need to find out how much is it over, or how much is it under? Okay. So here the bank statement is $53.54. Okay. Made a mistake here. that should be $15.49, not $15.48. I was off by a penny. So that means that this is going to be $39.51. Okay. And if I add $39.50 to the $50.59, that would mean I will have $60.10. Okay. So now that $53.54 is different from the amount in the checkbook. So I need to subtract $60.10 minus $53.54. Okay. So $60.10 minus $53.54. That's $6.56. Which means that the bank is under by that amount, $6.56. Okay, because the amount that's in the checkbook is more than the bank statement. Okay. The next page is another example. A stock rose 74 cents in the market on Thursday if the resulting price was 75.744. What was the price on the stock before the rise? So here we need to subtract here. Okay, so the resulting price was 75.744. And then we're going to subtract 74 cents from that. That would be 0.74. And notice I'm lining the decimal points. My decimal place is up. So that the decimal point is in the same position. In this case, I need to put a 0 here in 0.74. When I subtract, 4 minus 0 will be 4. 4 minus 4 is 0. 7 minus 7 is 0. Bring the decimal point down. 0 from 75 will be 75. So $75.004 represents the price of the stock before the rise. Okay. Okay, that's how we deal with adding and subtracting decimals. All right, now let's talk about multiplying decimals. An algorithm for multiplying decimals can be stated as follows. If there are n digits to the right of the decimal point in one number and m digits to the right of the decimal point in the second number, multiply the two numbers, ignoring the decimals, and then place the decimal point so that there are m plus n digits to the right of the decimal point in the product. So for a problem like, let's say 6.2 times 1.43, this is what I would do. I would put the 1.43 on top and then multiply that by the 6.2, since there are 3 digits in 1.43. And ignoring the decimal points, I'll multiply this out the long way, just like I would do any multiplication problem. Start with 2 times 3, that will be 6. And then 4 times 2 will be 8. 2 times 1 will be 2. Now, for the 6, I would use a 0 placeholder since I'm dealing with the next digit in front of the 2. 3 times 6, or 6 times 3 is 18. 6 times 4 will be 24, plus the 1 will be 25. Group with the 2. 6 times 1 will be 6, plus the 2 will be 8. Then we add our partial products here. This will be 6, 6. 1 plus 2 is 3, plus 5 is 8. Bring down the 8. Now, in this case, we need to count the number of decimal places in the first number. There are 2. In 6.2, there's one number behind the decimal point. Add 2 plus 1, that would be 3. So my final answer will have to be the number with 3 digits behind that decimal point. So that decimal point in this case will be behind the first 8. So my final answer there will be 8.88, 8.866, 8.866. All right, part B, 0.02 times 0.013. Let me put the 0.013 on top and then 0.02 on the bottom. And just go ahead and multiply. 2 times 3, that will be 6. 2 times 1 will be 2. Okay, now for the first number, there are 3 digits after the decimal points. The second number has 2 digits after the decimal point. Add 3 and 2 together, you're going to get 5. So my answer has to have 5 numbers behind the decimal point. Well, I got 2. I need 3 more, so I need to put zeros there. And I'll go ahead and put a 0 in front. So my final answer there will be 0.00026. And in part C, we got 1,000 times 3.6. Now, of course, you can do this the long way. Here, 6 times 0 is 0. And then 6 times 6 is 0, 0 zeros. 6 times 0 again is 0. 6 times 1 will be 6. 0 placeholder, 3 times 0 is 0. 3 times 0 is 0. 3 times 0 is 0. 3 times 1 is 3. Add your partial products, you'll get 36,000. But in 3.6, there's only one number behind the decimal point. So that means I need to put a decimal point in front of that last 0. So 1,000 times 3.6 will be 3,600. And notice 1,000 is the power of 10. In 1,000, there are 3 zeros. So that means I can take that 3.6 and move that decimal point 1, 2, 3 places. And I had to add 2 zeros there. So 3.6 times 1,000 would be 3,600. That's the other way I could have gotten that answer. All right, next we'll look at this one. A US $1 bill was valued at 0.9741 Norwegian kroner. That's Norwegian currency on a particular day. What was the value of $35.61 of American dollars in Norwegian kroner that day? Okay. Let's see. If I did $35.61 times 0.9741, I just go ahead and do this on the calculator. You'll see that it's 34.67687701. 34.687701. Now they might want you to round off to 2 decimal places in this case. So, and we're going to talk about rounding in a few minutes, but let's say to the nearest 100. The second number after the decimal point, that's the 8. The number to the right of it is 7. That's bigger than 5, so we're going to increase that 8 to a 9, so it'll be 34.69. So in this case here, in Norwegian kroner, it's going to be 34.69. Okay. All right, next we're going to look at scientific notation, how to convert from standard form to scientific notation and the other way around. Scientists use scientific notation to handle either very large or very small numbers. For example, the distance light travels in 1 year is this huge number, 5,872,000,000,000 miles, and that's called a light year. And we can express that in scientific notation as 5.872 times 10 to the 12th power. And then the mass of an electron, which is 0.00054,875 atomic mass units, we can express that in scientific notation as 5.4875 times 10 to the negative 4th power. Okay. Now, by definition, in scientific notation, a positive number is written as a product of a number greater than or equal to 1 and less than 10, and an integer power of 10. To write the negative number in scientific notation, we treat the number as a positive number and adjoin the negative sign in front as the result, in front of the result when we do get our final answer. All right, every number in scientific notation must be in the form of a times 10 to the power of n, where a is going to be some number that is at least 1 but less than 10. N must be a positive or negative integer. Okay. So here's how we convert from standard form to scientific notation. To convert a number to scientific notation, you're going to place or move the decimal point a number of units. Place or move the decimal points a number of places until the coefficient of the number is greater than 1 and less than 10. Is you're going to move the decimal point a certain number of places until you're able to get the number that is at least 1 but less than 10. Record down the coefficient, which is your A, and count the number of steps the decimal point was moved. And then the number of steps that was moved, which is going to be your n, is going to be taken as the exponent. Now, moving the decimal point to the right gives a negative exponent, whereas moving the decimal point to the left will make it a positive exponent. Okay. So let's look at some examples of this, like 413,682,000. And I want to write this in scientific notation. All right, so I'll rewrite this. All right, it's a whole number, so we need to move to the left. Okay, the decimal point is understood to be behind the very last digit in that number. So here we're going to move this decimal point 1, 2, 3, 4, 5, 6, 7, 8 places. You want to move it a certain number of places so that the first part will be a number that is at least 1 but less than 10. Okay, so the decimal point needs to be behind the 4. Or another way you can think about it is this: you want your decimal point behind the very first non-zero number. So the first part would be 4.13 times 10. Now notice that we moved the decimal point 8 places to the left. So that means that 8 will be your exponent for 10. So 413,682,000 in scientific notation would be 4.13 times 10 to the 8th power. Okay. Now, in part B, we have a decimal, 0.0000231. Let's put the decimal point behind the very first non-zero number in this, or the very first non-zero digit in that number. And that very first non-zero digit is a 2, so the decimal point will be behind the 2. So I know I'm going to have 2.31 times 10 to some power. From this decimal point to this decimal point that I place here, how many digits do we see here? There are 5. And we move to the right. So that means the exponent has to be negative. Okay. Another thing that you can think about is this. If you have a decimal like this and you convert it to scientific notation, the exponent has to be negative. If you have a whole number like this one, your exponent for the power of 10 will have to be positive when you're converting it to scientific notation. Now look at part C, we got 83.7. That number is not in scientific notation, okay? Because that is not a number that is at least 1 but less than 10 multiplied by a power of 10. So what we need to do here is put the decimal point behind the very first non-zero number from left to right. That decimal point needs to be behind the 8. So that means I'm going to have 8.37 times 10. Now, from this decimal point to this decimal point, how many moves did we make? Only 1. And it was 1 place to the left, so that power of 10, that exponent for 10 will have to be positive. So in scientific notation, it will be 8.37 times 10 to the first power. Now part D, negative 10 million. Negative 10 million. Okay, it's a whole number. We need to put the decimal point behind the first non-zero number. And it has to be behind the 1. So here, this will be negative 1. We can say negative 1.0 times 10. Now, the decimal point originally was behind this last 0. So from that decimal point to this decimal point, there are 1, 2, 3, 4, 5, 6, 7. We move 7 places to the left, so that means our exponent for 10 will have to be positive 7. Now, part E is a little bit different. 0.34 or 0.34 multiplied by 10 to the negative 6th power. You may think that's in scientific notation. It's actually not, because the first digit, this part right here, is not a number that is at least 1 but less than 10. So we need to change that. We need to put that decimal point behind the very first non-zero digit in that number. I need to put the decimal point behind the 3. So I'm going to have 3.4 times 10. So from this decimal point to that decimal point, I went over to the right 1 place. So when we move to the right, we're going to have a negative exponent. We only move one place to the right, so it has to be 10 to the negative 1. And I also got times 10 to the negative 6. I need to bring that down. Now let's simplify this. I have 3.4. Now I'm multiplying powers of the same base. So I need to add these exponents. So it'll be 3.4 times 10 to the negative 1 plus negative 6. That'd be negative 7. So in scientific notation, I will have 3.4 times 10 to the negative 7 power. Okay. All right, let's look at this example, similar to the homework. The distance between two planets is 25 billion miles. 25 billion meters. And I want to write that in scientific notation. $25 billion meters. Now we want to write this in scientific notation. It's a whole number, so I need to go ahead and put the decimal point behind the very first non-zero digit in that number. So that decimal point needs to be behind the 2. So I'm going to end up with 2.5 multiplied by 10 to the, now the decimal point originally was behind the last 0 in 25 billion. Now I'll place it here. So that means between this new decimal point and the old one, there are 3, 6, 9, 10. And I move 10 places to the left. That means that the exponent for 10 has to be positive. So it'll be 2.5 times 10 to the 10th power. Okay. All right. Now let's go the other way. Let's say we're given scientific notation and we want to convert those to standard form. So here we're going to look at the exponent of 10 in scientific notation. If the exponent of 10 is positive, you're going to move the decimal point to the right that number of places, whatever that exponent is. And if the exponent of 10 is negative, you're going to move the decimal point to the left that number of places, depending upon what the exponent is. Like in this example, 6.84 times 10 to the negative 5th power. 6.84 times 10 to the negative 5th power. So in this case here, that exponent is a negative. So that tells me I need to move this decimal point in 6.84, 1, 2, 3, 4, 5 places, because the exponent is 5 and it's negative. That would mean I need to put 4 zeros in front of the 6, 8, 4. So this is my answer in standard form. 0.00000684. Okay, that's my answer in standard form. Now for part B, 3.12 times 10 to the 7th power. 3.12 times 10 to the 7th power. Now my exponent for the power of 10 is 7. So that tells me I need to move the decimal point in 3.12 7 places to the right because it's a positive 7. So I'm going to move this decimal point 1, 2, 3, 4, 5, 6, 7. I need to add 5 zeros. So that means I'm going to have 312 with 5 zeros. And actually, this will be 31,200,000. 31,200,000. And in part C, I got negative, and this is a negative, 4.08 times 10 to the 4th power. All right, let's concentrate on the 4.08. And then on the final answer, I'll tackle on the negative sign. That 4 in the power of 10 is positive. So that tells me I need to move this decimal point 1, 2, 3, 4 places, meaning I need to put 2 zeros there. All right, so my final answer, I'll add the negative. This will be 40800. So it'll be negative 40,800. Negative 40,800. Okay, let's look at some homework examples here. Let's say we want to convert to standard form each of the following digits, scientific notation, and I want to convert them to standard form. And if you want to, you can pause the video and try to do these problems yourself. Then I'll give you the answer. Okay, so for part A, we got 3.1 times 10 to the negative 5th power. So now, in 3.1, the power of 10 is negative. It's a negative 5, so that tells me I need to move that decimal point 1, 2, 3, 4, 5 places. That will mean I need to put 4 zeros in front of the 3 and the 1. So 3.1 times 10 to the negative 5th would be 0.0000031. Part B. Let's say we got 3.1 times 10 to the 5th. Now this time, our exponent of 5 is positive. So that means I need to move the decimal point to the right 5 places. So in 3.1, I'm going to move this decimal point 1, 2, 3, 4, 5. Meaning I need to include 4 zeros. So this will end up being 310,000. 310,000. All right, part C, 4.7 times 10 to the negative 2 power. Well, my exponent for 10 is negative 2. That means I need to move to the left 2 places, move the decimal point 2 places to the left. So I need to include a 0 in front of the 4. So 4.7 times 10 to the negative 2 will end up being 0.047. And part D, 6.3 times 10 to the 4th. Okay, in this case here, my exponent for the 10 is 4. So in 6.3, I need to move that decimal point 4 places to the right because it's the positive 4. 4 places to the right. I need 3 zeros behind that 3. So 6.3 times 10 to the 4th would be 63,000. 63,000. All right, here's a homework example. Let's say the distance between a comet and a planet is 8.5 times 10 to the 6 kilometers, and we want to write this in standard form. Okay, so we got 8.5 times 10 to the 6. And in standard form, well, my exponent for the 10 is 6 is positive, so I need to move this decimal point 1, 2, 3, 4, 5, 6 places, meaning I need to add 5 zeros. Okay. that will mean that 8.5 times 10 to the 6 in standard form would be 8,500,000. Okay. All right, now let's talk about multiplying and dividing numbers in scientific notation. All right, on the left-hand side, you'll see the way to multiply numbers in scientific notation. In this case here, you're going to rewrite the multiplication expression to group the first factors and the powers of 10. Then you're going to multiply your first factors, then multiply the powers of 10 by using the product of powers property, meaning this: when you multiply powers of the same base, you write down that base and then you add your exponents. And then you rewrite the product to be in proper scientific notation if needed. That means if that first factor is not at least 1 but less than 10, then you'll have to write that in scientific notation. Now for dividing numbers in scientific notation, which is this on the right, you're going to rewrite the multiplication expression to group the first factors and the powers of 10. Then you'll divide your first factors, then divide the powers of 10 by using the quotient of powers property. In other words, when you divide powers of the same base, you're going to write down the base and then subtract your exponents. And then rewrite the product to be in proper scientific notation if needed. All right, so now let's look at these few homework examples that we have here, dealing with multiplying and dividing numbers in scientific notation. In this case here, part A, we got 6 times 10 to the 15th times 9 times 10 to the 17th power. I'm going to write this down here. Okay, so here we're going to group the first factors like 6 and 9. And that's going to be multiplied by grouping the powers of 10. 10 to the 15th times 10 to the 17th. So we multiply the first factors, which is 6 times 9, that's 54, times we multiply the powers of 10. Here we're multiplying powers of the same base, so we bring over the base of 10, add 15 and 17 together, you'll get 32. So we have 54 times 10 to the 32nd power. The problem with that is this first factor is not between 1 and 10. So we need to convert that 54 into scientific notation. And we're going to do that by putting a decimal point behind that very first non-zero digit in 54. The decimal point needs to be behind the 5. So 54 will be 5.4 times, I'm going to use a raised dot for the multiplication, 5.4 times 10. And we have one number behind the decimal point, so it has to be 10 to the first times 10 to the 32nd. Now we're not done yet. We need to bring down this 5.4, and we got 10 to the first times 10 to the 32nd. Well, multiplying powers are the same base, so we bring over the 10 and add 1 and 32 together, you'll get 33. So it'll be 5.44 times 10 to the 33rd power as the final answer written in scientific notation. Okay, take a look at part B. This one's division. Here we got 8 times 10 to the 11th divided by 4 times 10 to the 4th. So here we have a division problem here. So now we're going to group this by doing 8 divided by 4. And then that's going to be divided by 10 to the 11th divided by 10 to the 4th. I'll take that back. This will have to be times, okay? So I'm going to divide the first factors. 8 divided by 4 will be 2 times dividing powers of the same base. We bring down to 10 and subtract 11 minus 4. That will be 7. And with this problem, it is already in scientific notation. The final answer is already in scientific notation because 2 is a number that is at least 1, but less than 10. So the final answer there will be 2 times 10 to the 7th power. All right, part C is a combination of multiplication and division. 2 times 10 to the 7th times 2 times 10 to the 9th divided by 2 times 10 to the 11th. Okay, let's take each operation one at a time before we do anything. Let's start with this part right here. I'm going to group the 2 times 2, and then times, group the powers of 10, 10 to the 7 times 10 to the 9th. And then that's going to be divided by 2 times 10 to the 11th. I'll get to that part later. But I just want to focus on this right here. Of course, 2 times 2 is 4 times 10 to the 7 times 10 to the 9th. We're multiplying powers of the same base. So we bring down the 10, add 7 and 9, we'll get 16. And it's already in scientific notation. So it'll be 4 times 10 to the 16th. Then that's going to be divided by 2 times 10 to the 11th. Now let's focus on the division. Let's do 4 divided by 2, and then times 10 to the 16th divided by 10 to the 11th. Now in this case here, if we do 4 divided by 2, that will be 2 times 10 to the 16th divided by 10 to the 10 to the 11th. We're dividing powers of the same base, so we bring down the base of 10, subtract 16 minus 11, that will be 5. So we'll end up with 2 times 10 to the 5th power as our final answer. Okay. All right, next we'll look at dividing decimals. When the divisor is a whole number, the division can be handled as with whole numbers. The decimal point can be placed directly over the decimal point in the dividend, like in this number, 128.60 divided by 4. Now notice here, they place the decimal point directly above this decimal point in our dividend. And then went through the division by doing 4 goes into 12 3 times. 3 times 4 will be 12. That's 0. Bring down the 8. 4 goes into 12. 4 goes into 8 2 times. 2 times 4 will be 8 with 0 left over. Bring down the 6. 4 goes into 6 1 time. 1 times 4 will be 4. 4 from 6 will be 2. Bring down the 0. 4 goes into 25 times. 5 times 4 will be 20 with a 0 remainder. So the quotient there will be 32.15. All right. Now, let's say that the divisor is not a whole number, as in 101.2032 divided by 0.32. Here we can obtain a whole number divisor by expressing the quotient as a fraction and then multiplying the numerator and denominator of the fraction by 100. Now this corresponds to rewriting the problem in the form A as an equivalent problem in the form B as follows. Here's the original problem. From this, it will be converted to this. And this is what they did. They moved the decimal point 2 places to the right to make it a whole number. You have to move the decimal point a certain number of places so that your divisor will end up being a whole number. And in this case, they moved the decimal point 2 places to the right. Well, if I'm going to do that, then I also have to move 2 places to the right in the dividend as well. So whatever number of places you move to the right in your divisor, you have to move the same number of places for your decimal point in that dividend as well. And then we go through the division. So 1.2032 divided by 0.32 would end up being 3.76. Okay, now, let's say I want to compute the following here. I'm going to use long division in this case. So here I got 13.169 divided by 0.13. Okay. Now I want to make that divisor a whole number. So I need to move this decimal point 2 places to the right because I want that a whole number. Well, if I'm going to move that decimal point 2 places to the right here, I got to do the same thing here. Move this decimal point 2 places to the right. So the decimal point would be behind the 6. Now I'll pull the decimal point straight up in that quotient. And now we're going to do the long division. If I take 13 into 13, that will go 1 time. 1 times 13 is 13. 13 from itself is 0. Bring down the 1. Can 13 go into 1? No. So it's got to be a 0 here. 0 times 13 is 0. You'll have 1 left. Bring down the 6. 13 goes into 16 1 time. 1 times 13 will be 13. 13 from 16 is 3. Bring down the 9. And then 13 goes into 39 3 times. 3 times 13 will be 39. 0 left over. So my final answer there will be 101.13. I mean 0.3. 101.3. All right, let's try this one. 9 divided by 0.75. So my divisor will be 0.75. 9 will be here. Now in this case, to make that divisor a whole number, I need to move this decimal point 2 places to the right. Well, if I'm going to do that, I need to move the decimal point in the 9 2 places to the right. So I need a decimal point here, because that's where the decimal point is understood to be in a whole number. I might have to add 2 zeros here. So I can move that decimal point 2 places to the right. And here's where the decimal point will be in the quotient. So now, we're going to do our division. Let's start with dividing 75 into 90. That will go 1 time. 1 times 75 will be 75. Subtract 75 from 90, you'll get 15. Bring down the 0. 75 into 150 will go 2 times. 2 times 75 will be 150. 150 minus 150 is 0. So 9 divided by 0.75 would be 12. Okay. Let's take a look at this homework example. Let's say I went to the store to buy canned tuna. these are the sizes and prices for each brand. Which is the best buy based solely on cost per ounce? So here we got brand A with 10 5-ounce cans for $11.50. Brand B has 8 5-ounce cans for $6.80. Brand C has 12 5-ounce cans for $40.80. And brand D has 3 5-ounce cans for $2.10. And here I want to find out which is going to be the best buy. In other words, which one would be the cheapest cost per ounce? The cheapest. So in other words, I need to do some division here. Now, for brand A, that would mean I need to do $11.50, divide that by 5. Okay. I'm sorry, by 10. 10 5-ounce cans. They're all 5-ounce cans. But in this brand A, you have 10 5-ounce cans. Now, I'm going to go ahead and use the calculator for the sake of time. So it'll be $11.50 divided by 10. This will be 1.15. So each can for brand A is $1.15. And now for brand B, you have 8 5-ounce cans for $6.80. So $6.80 would be divided by 8. So 680 divided by 8 would be 0.85 or 85 cents per can for brand B. Now for brand C, $40.80 for 12 5-ounce cans. So $40.80 divided by 12 would be 3.40, which is in this case $3.40 per 5-ounce can. And then finally for brand D, $2.10 for 3 5-ounce cans. So $2.10 divided by 3.7 or 70 cents a can. All right. So based on cost per ounce, and actually, this is actually cost per can. They probably want this for cost per ounce. So for something like this, I need to look at dividing each one of these by 5 ounces. So this is going to be cost per can. So for each can is 5 ounces. So if I take $1.15, divide that by 5, this will be 0.23. So brand A has a cost of 23 cents per ounce. And this is 85 cents per can for brand B. So 0.85 divided by 5 would be, and I'll write this out, 0.17. So 17 cents per ounce. And then brand C is $3.40 for 5 ounces. $3.40 per can for a 5-ounce can. Oops. This will be 68 cents per ounce. And then the last one was 70 cents per can divided by 5. Would be 0.14 or 14 cents per ounce. Now, by looking at these numbers here, the smallest or the cheapest would have to be the one that's 14 cents per ounce. Okay. So that means that brand D is the best buy. Okay. And that's because it's 14 cents per ounce. Okay. Now these numbers represent cost per can. And each can is 5 ounces. So I have to divide each one of those cost per can by 5 ounces for the cost per ounce. Okay. A car went 258 miles on 13 gallons of gas. How many miles to the gallon does the car get rounded to the nearest mile? Now, of course, we can do the long division if we like by dividing 13 gallons into the 258 miles to get the number of miles to the gallon or miles per gallon. Well, if I divide 13 into 25, that's going to go one time. 1 times 13 is 13. 13 from 25 will be 12. Bring down the 8. And in this case here, 13 goes into 128. I would say 9 times. 9 times 3 is 27. Carry the 3. 1 times 9 is 9. Plus 3 is 12. 127 from 128 would give me 1. Okay, so in this case here, we're looking at approximately 19 miles per gallon if we were to round this off to the nearest mile. Okay. Now, of course, we can verify that using the calculator. 258 divided by 13. Actually, it's 20. Now, mine are messed up here because that's 12. Bring down the 8. 13 times 9. Actually, it's 117. That would give us 11. Okay. And 11 is close to 13. So if I was to extend this, bring down the 0, 13 goes into 110, 8 times. This will be 24, carry the 2. 19.8 would round off to 20 miles to the gallon. 20 miles to the gallon. All right, here's another homework example. Julia cut a string of 509.28 meters long into 24 equal pieces. What is the length of each piece of string? So we're going to divide 24 into the 509.28. Bring the decimal point up since the divisor is already a whole number. 24 goes into 50 2 times. 2 times 24 would be 48. 48 from 50 is 2. Bring down the 9. 24 goes into 29 1 time. 1 times 24 is 24. 24 from 29 would be 5. Bring down the 2. 24 goes into 52 2 times. 2 times 24 will be 48. Subtract 48 from 52, you'll get 4. Bring down the 8. 24 goes into 48 2 times. 2 times 24 is 48. 0 remainder when you subtract. So here, the length of each piece of the string is 21.22 meters long. 21.22 meters long. Okay. All right, now let's look at mental computation. Here's some tools for doing mental computation with whole numbers, and they can be used with decimal numbers, like breaking and bridging. So if you have something like 1.5 plus 3.7 plus 4.48, take 1.5 and add the 3 to it, you'll get 4.5, and then that 0.7, and then plus 0.4, then plus 4.48. Add 0.5 to 0.7, or 4.5 to 0.7, you'll get 5.2, then plus 4.48. Add the whole number 4 to the 5.2, you'll get 9.2. Then 9.2 plus the remaining 0.48 will give you 9.68. So that's how we use breaking and bridging to add decimals. Okay. Number 2 will be using compatible numbers. Decimal numbers are compatible numbers when their sum gives you a whole number, like 7.91, 3.85, 4.09 plus 0.15. If I add 7.91 and 4.09 together, I get 12. 3.85 and 0.15 would give me 4. 12 plus 4 is 16. Okay. Now, if we want to make compatible numbers, this is number 3, 9.27 plus 3.79. I will break 9.27 as 9.25, and then the rest is going to be 0.02. For 3.79, break that up as 3.75 plus 0.04. These are compatible numbers, so 9.25 plus 3.75 will give me 13. And then 0.02 plus 0.04 will be 0.06. 13 plus 0.06 will be 13.06. Then the 4th would be balancing with decimals and subtraction. So I would add both the top and the bottom numbers using some number that will give me a whole number. So for 4.63 minus 1.97, if I add 0.03 to the 1.97, I would get 2. But I also had to add 0.03 as well to that 4.63, you'll get 4.66. So 2 from 4.66 will be 2.66. Okay. So that's how we balance with decimals when we're doing subtraction. And what about division? 8 divided by 0.25. Well, let's make that divisor a whole number by multiplying 0.25 by 4 to get 1. And also, we'll have to multiply 8 times 4. That would give us 32. So 32 divided by 1, guess what? You'll get 32. So those are just some strategies that we can use, or mental math strategies that can be used with problems like these. All right, now let's look at this example. Johnny worked a 16-hour work, well, a 16-hour week at $6.25 an hour. Mentally compute his salary for the week and explain how you did it. Now, of course, there are ways that we can come up with that answer. But 16 times 6.25. This is what we can do. We can think of 6.25 as 6 plus 0.25. Break that up like this. That's the sum of 6 and 0.25. And then this is what I would do. 16 times 6. And then 16 times 0.25. Okay, so 16 times 6 will be 96 plus, think of 25 as 1/4. 1/4 of 16 will have to be 4. And then 96 plus 4 ends up being, of course, 100. And if we were to round to the nearest cent, they want this, 100.00. So Johnny was paid $100. Okay, now on the next page deals with rounding decimals, similar to rounding whole numbers. Rounding is a process to estimate a particular number in a context. To round a number, look at the next digit in the right place. If that digit is less than 5, you're going to round down. And if the digit is 5 or more than 5, you're going to round up. Okay. So let's say we have 766.284, and we want to round to the nearest hundred, to the nearest tenth, to the nearest unit, or the ones place, to the nearest 10, and to the nearest hundred. Let's start with the nearest hundred. We find the digit that's in the hundreds place. That's going to be this 8. The number to the right of that, or the digit to the right of the 8, is 4. Here, 4 is less than 5, so we round down, meaning that this 8 remains the same. So we're going to have 766.28. We drop off the number that's behind the number that we're rounding off to. Now, the same number to the nearest tenth. This time we look at the digit that's in the 10th place. That's the 2. To the right of that is 8. Here it is 5 or more than 5. So we're going to round the 2 up to the next digit, which is a 3. So it'd be 766.3, and the other numbers behind it, we drop off. All right, now to the nearest unit, or to the nearest whole number, as some textbooks would say. Well, we look at the digit that's in the ones place. That's this 6 right here. To the right of that is 2. The 2 is less than 5, so the 6 remains the same. So we'll just say 766. The 2, the 8, and the 4 are dropped off completely. Now to the nearest 10. The digit in the tens place in this number is the 6. The first 6 is the digit in the tens place. To the right of that 6 is the other 6. Here it is 5 or more, so that means we need to increase this 6 to a 7. So we're going to have 7, 7. This 6 in front of the decimal point will change to 0. The numbers after the decimal point are taken off. And to the nearest hundred. where the digit in the hundreds place is a 7. To the right of that is a 6. That 6 is 5 or more, so we increase the 7 to an 8. The 6 and this 6 in front of the decimal point changes to zeros. To the right of that, the numbers after the decimal point are dropped off. So 766.284 to the nearest 100 would be 800. Okay. All right, now let's look at estimating decimal computations using rounding. Rounded numbers can be useful for estimating answers to computations. When computations are performed with rounded numbers, the results may be significantly different from the actual answer. Other estimation strategies, such as front-end clustering or grouping to nice numbers that were investigated with whole numbers, also work with decimals. So let's look at this homework example number 14. John wants to buy some camera equipment. To estimate the total cost, he rounds each price to the nearest dollar and adds the rounded prices. What is his estimate for the items listed? So in this case here, we got a camera for $72.36. And then the film, $28.86, and the case is $1.93. So he's going to round each of these answers to the nearest dollar, and then we're going to add those rounded prices. So the camera, $72.36. To the nearest dollar, we look at the digit in the ones place, that's the 2. To the right of that is the 3. That's less than 5. So the camera's cost will stay at $72. Film is $28.86. The digit in the ones place is an 8. To the right of that is 8. That's bigger than 5, so we round up from 28 to 29. $1.93 for the case. The 1 is in the ones place. To the right of that is 3. We increase the 1 to a 2. So we're going to add those 3 digits, $72, $29, and $2, which will be, in this case, $103. So the estimate for the items listed here would be $103. And by the way, we're adding here. Okay, finally, the homework example number 15. Here we're going to estimate the sum or difference in each of the following using rounding and front-end estimation, and then perform the computation to see how close your estimates are to the actual answers. Okay. So this might take a while for this one. Here we got $67.99, 28.93, 14.42, and 17.03. Okay. Okay, so if we were to estimate by rounding, in this case, let's say by rounding, and I'm not sure how they want us to round in this case. So let's see, they probably want us to round these answers to the, let's say, to the nearest whole number. Actually, I'm looking at the homework, they're going to say to the nearest 10. In this case, to the nearest 10. All right, so we have to look at the digits in the tens place and then look at the number to the right of it to round up or down. $67.99 will have to round up to 70. $28.93 to the nearest 10 will round up to 30. $14.42 to the nearest 10 will round up to 10. And then 17.03, we'll round up to 20. Okay, because I'm rounding to the nearest 10. So if I add 70 and 30, that's 100, plus 10 is 110, plus 20 would be 130. So that sum would be $130. I mean, 130. Now, let's say we were to use what they call front-end estimation. Front-end estimation. Okay, that would mean I need to look at probably these numbers right here, and then look at the decimal points behind it, okay, to get a better estimation. Now, if I had 67.99, that will probably be 68. This will be probably 29. This will be probably 14, and this will be 17. So 68, 29, 14, and 17 would be 128. So if I was using front-end estimation, that would be 128. That would be just part A, okay? And the way I did that, I just rounded these numbers to the nearest whole number. So that's part A. Part B, 86.48 minus 33.14. Now, if I was to round these off to the nearest 10, this is what I would do. Look at the digit in the tens place in part B. The 8, the 6 will make that 8 a 9, so it'll be 90, minus the 3's in the tens place, another 3 is right behind it. That will keep the 3 as is. So it'll be 90 minus 30, which will be 60. Okay, and if I use front-end estimation, probably if I look at 86.48, I would say 86, round that down by looking at the digit that's in the 10th place for each one of those to determine whether I need to round up or down. Then 33.14 to the nearest whole number, that would be 33. Subtract 33 from 86, you'll get 53. Okay, so using front-end estimation, that would be 53. Okay. Now for part C, 5.27, 6.17, 9.89, 4.19. If I was to look at the numbers that are in the ones place in this case, because that's probably going to be the best that I can do with that one. So if I was to do an estimate for that, 5.27 to the nearest whole number will be 5. 6.17 to the nearest whole number will be 6. 9.89 to the nearest whole number will be 10. And 4.19 to the nearest whole number will be 4. So if I was to add these numbers together, you'll get 25. So by rounding, it'll be 25. Now, using front-end estimation, I will look at the number that's in the 10th place on each one of those and round up or down. So 5.27 will round up to 5.3. 6.17 to one decimal place will round up to 6.2. 9.89 rounded to one decimal place will be 9.9. Then 4.9 rounds up to 4.2. So if I was to do 5.3 plus 6.2, 6.2 plus 9.9 plus 4.2, I would get 25.6 using front end estimation. Okay. And then in part D, it's 221.38 minus 87.35. Now, if I was to round this, let's say to the nearest 100. I look at the first digit, which is a 2. To the right of it is 2, so that stays at 200. 87.35, that's going to be close to 100, so I round that up to 100. 200 minus 100 would be 100. Now, if I did front end estimation, I would be looking at the digit in the ones place. So 221.38 will round to the nearest whole number, 221. 87.35 rounded to the nearest whole number would be, let's see, 87. And 221 minus 87 would be 134. That would be using front end estimation here. Now, of course, in these problems here, they do want the actual numbers to see how close you are. So in part A, if I did 67.99 plus 28.93 plus 14.42, 14.42 plus 17.03, the actual number would be 128.37. I'm going to do this in a different color. So the ones in green are the actual numbers, 128.37. You can see how close that is to those estimates. And then part B, 86.48 minus 33.14, that would be 53.34. That's the actual number, actual difference. That's closer to the front end estimate. And then in part C, 5.27 plus 6.17 plus 9.89 plus 4.19 would be like 25.52. Okay. So pretty much those estimates are the same, are pretty much close. And then finally that 221.38 minus 87.35 would be like 134.03. So that's close to our front end estimate there. Okay. So that's how we do that particular problem there. Not only you have to use rounding and front end estimation, you have to come up with your actual values here, those differences, just to see how close you are to them. All right, so that does conclude or complete this video on section 7.2 dealing with operations on decimals. Feel free to email me if you have any questions about anything presented in this video or any of the homework that's in my math lab.